Okay, so we need to now start thinking about moving energy from energy surplus places to energy deficit places. Obviously, from on a sphere, it's from low latitudes to higher latitudes. Let's now imagine, for understanding's sake, that the Earth is standing straight and not rotating around its axis, and the Sun is going around, so the energy is being distributed but without Earth's rotational effect. So you still have deficit energy at high latitudes and excess energy at low latitudes. And remember, excess energy creates warmer temperatures. Air rises, so you can see rising air. And we still have the vertical structure because we are still providing our standing planet with oxygen and spectrum of electromagnetic radiation from the Sun. So we still have tropopause, and the rising air is going to hit the ceiling and go towards the poles everywhere at each point, right? So what happens because of non-rotation? The cold temperatures are going to have high pressure, warm temperatures are going to have low pressure, so warm air is going to rise, requiring air to come in, and it will come in from the latitudinal direction because we are assuming the Earth is, let's say, uniform, no differences in continents, oceans, etc., for simplicity. So air can directly flow from high pressure to low pressure because there are no rotational effects. It's just going to make it to the equator and fill in the rising air that is leaving the surface. That rising air is going to go all the way to the pole, and we still have this latitudinal decrease in tropopause height because we still have the increasing density, colder temperatures, and denser atmosphere, and smaller atmosphere in altitude. Okay, so this would be the simple case. But now we know that we are on a planet that's rotating around its axis. It's also tilted, so we'll add the tilt later. But let's start by looking at what rotation actually does. Many of you probably have learned it somewhere, Coriolis effect, but I'll go through it for those who may not have been exposed to it before. The simplest thing to again remember is Earth is a sphere, which means an air parcel or a piece of land or a person standing on the equator has to cover a much larger circumference in 24 hours than, let's say, Santa Claus standing here, or somebody standing here in cold Canada, or somebody standing here in La Paz, Mexico, or Baja California, and so on, right? Because the circumference is getting smaller and smaller as you go towards the pole, and it's zero on the pole. Okay, so anything that's moving here is moving at 1600 kilometers per hour. As you go to 30 degree north or 30 degree south latitude, that drops to 1400 kilometers per hour, depending on the distance you have to cover. And at 60 north, it's 800 kilometers per hour, so it's not a linear drop here. 200 kilometer per hour drop here, 600 kilometer per drop here, and 800 kilometer per hour drop to the North Pole. How do we use this? Let's say we are launching something from Galapagos towards New Orleans. Let's say it's a rocket full of chocolates for good intention to help people of New Orleans. So the rocket is moving northward because you've given it energy boosters, rocket engines to take it north, but it has also acquired the eastward 1600 kilometer per hour speed because it's being launched from the equator. And let's say there's no friction and it's going to be able to keep this eastward velocity it acquired because of Earth's rotation. Then as it goes towards New Orleans, then New Orleans is moving only at 1400 kilometers per hour towards the east, whereas the rocket is moving at 1600 kilometers per hour towards the east. So the rocket is going to get ahead of New Orleans by the time it reaches from the equator to New Orleans. So it's going to have an eastward displacement, eastward tilt, eastward detour because of Coriolis effect or because of rotational effect. So the best thing to remember, if you cannot understand the mechanisms, is that everything that moves in the northern hemisphere is tilted to the right of its direction of motion. So it's going north, it's going to be tilted eastward. If it's going east, it'll be tilted southward. If it's going west, it'll be tilted northward. So similarly, you have to flip it because southern hemisphere is pointing the other way. Coriolis effect is the opposite, so everything is tilted to the left of the direction of motion in the southern hemisphere. So you can see this also in another example where Santa Claus is launching a rocket full of gifts towards New Orleans, and he has 0 km/h velocity. So New Orleans has 1400 km/h, so New Orleans is going to get ahead of Santa Claus's rocket, or let's say reindeer, because it started with 0 eastward velocity or westward velocity. So it's going to fall behind, which means it is again tilted to the right of the direction of motion. It's easier to understand the north-south motion because the velocity is changing here, but similar thing happens if you move east-west. It is related to the centrifugal force you experience when you are going around, let's say on a merry-go-round, and that can be split into a rightward force and a force that is pointing towards the center of the earth, which is in the direction of gravity. So that component of the Coriolis effect in the direction of gravity is tiny, 1,000th of the gravitational pull, so we don't feel it much, but the remaining component, which is to the right of direction of motion, is still going to tilt you to the right in the northern hemisphere and to the left in the southern hemisphere, even if you move east-west. So the rotation affects things when they move at large enough scale, or anything actually, but it is detectable when you move at planetary scales, whether you move north-south or east-west. Okay, this is very key to remember. Now, look at this again. Non-rotating Earth, things can go directly from the North Pole to the equator, as we said, and on a rotating Earth they will get in the northern hemisphere tilted to the right of the direction of motion. Just remember that, to the right of the direction of motion. So here is again to reinforce North Pole here, northern hemisphere. So the other thing you didn't notice probably very clearly here is this tilt is not as large as the tilt here. Why? Because this has traveled much more distance, from 90° north to 30° north, so that is 60 degrees of latitude, whereas here you only traveled 30° north. So how much you get deflected depends on how far you travel, and we'll see later on that it also depends on how fast you travel, because the Coriolis effect is proportional to the speed with which you are moving. Okay, so that's kind of being made clear here. So if you're just starting it at an initial time here, after 4 hours you're tilted a little bit. After 8 hours there is a larger deflection. Okay, so just understand it. So if you're taking a flight from there to there, the airplane has to constantly adjust for the Coriolis effect, just as the rocket would have to adjust its direction constantly to stay on target. Okay, and at 30 north compared to 60 north, the Coriolis effect is smaller. So, but still, you can see that the deflection is smaller here and is also smaller here. Why? Because the Coriolis effect is 0 here, no deflection, initial time, 4 hours later, 8 hours later. Because the distance from the axis to the surface is getting smaller, circumference is getting smaller, velocity is getting smaller, Coriolis effect increases with latitude and its maximum at the pole. Largest deflection would happen here, and the tendency to rotate goes the same way. If you're here, you don't have, you're going in a linear sense, so you don't have head spinning, but as you go northward, the tendency to rotate increases, or the verticity, planetary verticity, increases. There is a concept of planetary verticity, which is the rotation because of the Earth's rotation itself, and there is what is called relative verticity. For example, hurricanes and cyclones are rotating faster than the Earth, so they have a relative verticity. In general, when you get into details of dynamics, you worry about total verticity, potential verticity, and so on and so forth. So I will introduce those concepts as we go along. So things to remember: things are tilted to the right of the direction of motion in the northern hemisphere, to the left of the direction of motion in the southern hemisphere, and the tilting or the deflection from the direction of motion is greater as you go from the equator towards the poles. On the equator there is no Coriolis effect. Okay, it's simple, easy enough to remember. So here is another way to look at it. So if you're going in this direction to the right, this direction to the right, this direction to the, so blue is the direction you're trying to head for, and Coriolis is tilting you towards the red line. So to the right, here, to the left, to the left, to the left, to the left. So you can just make a song out of it, right? Okay, so this leads us to a very interesting concept called geostrophic balance, which is very key. Maybe I should leave it for the next podcast because this one has already become 11 minutes. So just listen to it, make sure you get a good handle on Coriolis effect, and then we'll see how dynamics is seriously affected by Coriolis because we are on a rotating planet. Okay?